Hello students, welcome again. So I'm glad to announce that the response that I'm getting through messages, it's quite amazing. So I'm just sharing this with you. So you all are loving my lectures and learning thoroughly. So let's accelerate the series, and in that the first topic that we are taking today is electric potential due to a point charge. So as we have earlier defined, the electric potential at a point inside the electrostatic field is basically the amount of work done per unit test charge in bringing it from infinity to that particular point without any acceleration against the force of repulsion given by the source charge to it. So let's use this definition and try to find mathematically what is the expression for the electric potential due to a point charge. So let's begin. So here, suppose we have an isolated positive charge as the source charge situated here at O, and let this be plus Q, and right from here at certain point P we want to calculate the potential. So the distance of this point P from the source charge is small r, and let this be the point B, which is at distance of say not A, not this B, let we have the distance of point A from the source charge to be the X distance, and let we place test charge Q0 at the position of point A at distance X from the source charge, and let this Q0 test charge has been brought from infinity. So when this test charge is placed at A in the electrostatic field of this source charge, so this source charge will apply force of repulsion to this, which will be radially outward along this line. So that force of repulsion will be along this, and we will be shifting this test charge against this force of repulsion through displacement, say dx. So this is the small displacement that we will be producing without any acceleration on this test charge. So what is the amount of work done to produce this displacement? That will be calculated, and later on, just integrating that small amount of work done, taking the limit from infinity to finally r, we can have the required or desired expression. So let's begin by Coulomb's law. Coulomb's law, the electrostatic force on charge, or I must write test charge, on test charge Q0 is. So at this point, what is the electrostatic force? We can directly write using Coulomb's law, F equals to 1 upon 4 pi epsilon naught Q source charge into test charge upon this distance square. What is the distance of this test charge from the source? It is x. So x square. Now let this be displaced through small displacement dx. So the amount of work done. Now the work done to produce small displacement displacement dx is dw, which is equals to f dot dx. So as can be seen, force is acting along positive x and displacement is being produced along negative x. So the angle between them would be 180. So you can write it as f dx cos 180, and cos 180 we have minus 1. So this now finally comes out to be minus f dx. Now just having this value back here, we can have that dw to be, so this dw now comes out to be it is minus q naught upon 4 pi epsilon naught. Now that dx upon x square. So this dx upon x square, this has been taken over this. So final outcome is this. Now let me integrate this equation on both the sides, taking the limit from infinity to r finally. So the total work done, in bringing q naught from infinity to p is w, which is equals to minus q naught upon 4 pi epsilon naught, as this is a constant term, so it has got nothing to do with this integration, so I am just writing it out of the integration. Now the limit for this variable x is from infinity to finally r. So here I am writing infinity to r. So this is dx upon x square. So when you just integrate it, you'll have minus 1 by x. So that minus 1 upon x as the integration of this, and limits would be from infinity to r. And this is already minus q naught upon 4 pi epsilon naught. This is amount of work done. Now dividing both the sides by q naught test charge, this is minus q upon 4 pi epsilon naught. Here when you just have this negative sign out, so this gives plus, and just placing the limits will be having 1 by r minus 1 by infinity. So as we have 1 by infinity to be 0, so this finally gives us, this is basically what? The potential at point P. So I'm just directly writing it as V potential at P. So this is 1 upon 4 pi epsilon naught q by r. So this is the required expression that we have. This is one way students you can go through, or there is an alternate method. The alter way that we can proceed, alter way method. So what can we have? Here we will be using the very basic definition of electrostatic potential that we have as the first topic of this chapter. So suppose this is the isolated charge kept here at position O, and let we have here 2 points in the electrostatic field of this source charge, and those 2 points are namely A and B. And suppose the charge is right here, and as the charge is moved towards this through the displacement say dl, so this is vector dl, I am just writing now, and here actually the force of repulsion would be along this. So or else you can write the electrostatic field of this source charge will be radially outward at this point A. and the test charge will be moved towards V through dl against this. So the angle between them would be 180, and let me write the position vectors of this, or the separation of these points from this source charge. Let this be RA and this be, say, RB, and finally we want to have our test charge. We will be writing actually the potential difference between these 2 points, that is VA minus VB, using that first definition. And suppose this is the point which is R distance apart. Fine. So here, since we have, what do we have for the potential difference? VA minus VB, which is equals to minus integral from A to B vector E dot dl. So this is basically the potential difference that we derived in the previous lecture between 2 points inside the electrostatic field. So now here actually this dl is just equals to minus of dr. Why am I writing this? Why am I writing this? dl equals to minus of dr, as dl, when the test charge approaches towards the source charge, so this length decreases. As dl increases, dr or r decreases. So for that reason I am putting negative sign here. Understood? Okay. So here, so just placing here this back, we can have this negative sign, and this negative will make plus A to B vector E dot vector dr. Now further we can write it to be equals to say this, instead of, as we are writing this to be dr, so better to write these A and B in terms of distances. So that will be RA and this RB. Fine with this? Now we will be writing the electrostatic field intensity at this position, and later on just having the integration of that we can have potential difference. So let's have this Q upon 4 pi epsilon naught as the value of electrostatic field intensity. So here it is RA and RB. So this is actually 1 upon R square dr. See here, electric field intensity in dr is thereafter they both are along the same direction here. So for that reason we are having it to be positive. Understood? Okay. So now let's move on, and just placing the value here, having the integration of this, we can have VA minus VB, this thing, and this I must write VA minus VB here as well, so that there is no confusion at all. And on RHS you will be having Q upon 4 pi epsilon naught. Now just having the integration of this, we will have minus 1 by R, and here RE limit and then RB limit. So here just placing the limits, you may take this minus sign here out, Q upon 4 pi epsilon naught. So just having now 1 upon RB minus 1 upon RA. Okay, fine. Now let's have a look on this. Actually here in the first step, just to avoid the confusion, let me first solve this. So here actually electric field is here and dl is here. So the angle between them is 180. So EdL cos 180 will make minus EdL. So for that reason it becomes A to B EdL simply. Now when you just place the value of dl to be minus dr here, so this term is going to be negative. Clear? Okay. Now just continuing with this negative sign, here we can have negative. Now when this negative comes out, it makes it positive and rest thing remains as it is. Now here let me have this A point to be at infinity, where the potential is supposed to be 0. So just having this term VA to be 0, we can have let point A is taken at infinity, where potential is supposed to be 0. So actually here it is VB minus VA, it should have been. So just make correction, it should be VB minus VA, not VA minus VB, as we are having this point facing towards source charge and this is beyond this. So VB minus VA, it should have been, it's a correction. So VB minus VA, and later on we can have let point A is taken at infinity where VA is 0. Then here just placing 0, we have VB to be equals to plus Q upon 4 pi epsilon naught, it is 1 upon RB minus 1 upon infinity, as you place that becomes 0. So this dropping now dropping subscript B, we have, what do we have in general? Potential at certain point distant r from the source charge, 1 upon 4 pi epsilon naught q source charge upon distance r. So this is next way. You can come to this final step by either of the ways that we have just now discussed. Okay students, so let's have few discussions on the last result that we have obtained under this topic. So let's have discussion. For the discussion is first point, we can see that if the source charge is positive, so obviously the potential at certain point due to that source charge is going to be positive, and if source charge is negative, then obviously potential is going to be negative. Potential is positive as well as negative depending upon the type of source charge that we have. But still it is a scalar quantity, remember students. Okay, so if Q is greater than 0, that is positive, it implies V is positive, and if Q is less than 0, so it implies that V is negative. That is, V is positive as well as negative, but still it is a scalar quantity. Okay students, so don't make any confusion. Electrostatic potential is a scalar quantity. Okay, so let's have the second discussion point. Electrostatic potential at certain point at any point, I must say, at any point at a fixed distance from the source charge is found to be constant, uniform, same. Hence, we can say the electrostatic potential is spherically symmetric around the source charge. So here we can write that electric potential due to positive point, due to a single charge has spherical symmetry. Okay, now for the next point, third, we can have the variation. As we have seen, the potential is directly proportional to 1 by r, distance. So if the source charge is positive, so we can have the variation of electrostatic potential for source charge as well as source charge to be positive as well as negative. So here for positive it goes like this, varies like this, and for negative it varies like this. So these are the discussion points. So let's move on. Okay students, so let's have next topic, superposition principle for electrostatic potentials. As we had superposition principle for Coulomb's electrostatic force, later on superposition principle for electric field intensity. Now it's turn to have superposition principle for electrostatic potential. It means we will be having actually presence of multiple source charges, and in that multiple presence of source charges at certain point, what is the amount of electrostatic potential that we will be calculating here under this topic. So let's begin. Suppose we have two source point charges, I must write, positive in nature, Q1 and Q2, and in the mutual combined electrostatic field of these two source charges, let me have 2 points, point A and point B. Let us choose an arbitrary path L joining these 2 points. Now here at point P on this curve L, we want to have electrostatic potential. So let me first have the electrostatic field intensity due to this positive source charge at P. So here the electrostatic field intensity due to this positive source charge Q1 will be directed along this, and let me just make this vector E1. Now later on, due to this Q2 source charge, the electrostatic field intensity at point P will be directed along this. This is vector E2. Now as can be seen, these two are vectors acting along two different directions at single point, forming two consecutive sides of parallelogram. So we can have the application, or using that parallelogram law of vectors addition, we can find the resultant electric field intensity here. So to have that, let me just first complete this parallelogram so that we can draw the diagonal. So along the diagonal we can have the resultant electric field intensity. Fine with this? Okay, let's move on for the calculation part. So here actually we can write the electrostatic potential difference. Let's begin with the electrostatic potential difference between these 2 points. It's VB minus VA, which is equals to minus integral from A to B vector E dot vector dl. Fine with this? This is very basic definition that we have in the first lecture. Now later on, since using principle of superposition, we can have this E to be since vector E equals to vector E1 plus vector E2. Now just placing these values back here, so we can have minus of integral from A to B vector E1 plus vector E2 dot vector dl. Now just having separation of terms, we can have integral from A to B of vector E1 dot dl minus integral from the same A, B, E2 vector dot dl vector. So this is one potential or potential due to a single charge, and this is potential due to a second charge. So hence in the next for the next step, what can we write now? We can actually write here, just to make it more clear, we now take a point to be at infinity. Okay, so if say if a is taken at infinity and dropping the subscript b, we have, see, as you take this point to be at infinity, so this potential at infinity has to be 0. We have Vb on LHS, and dropping this B subscript, we have only V. So this V now is equal to minus of integral from infinity to B vector E1 dot dl minus this integral from, actually you can write it plus and put a bracket here like this, from infinity to B vector E2 dot dl. So it's quite clear that this is the potential due to first charge at point B, and this is the potential due to second charge at point B. That means we can write it V equals to V1 plus V2 as well. So that's it. Let's have next topic, electric potential due to a system of point charges. Here actually we'll have an assembly of n number of charges, and in that n number of assembly of charges we will consider single point, and at that particular single point what is the contribution of each and every charge forming the assembly of charges in terms of electric potential at that point under consideration. That will be calculated here under this topic. So let's start. Suppose we have here an assembly of n charges, and those are Q1, then Q2, Q3, Q4, Q5, and here suppose Qn. So these are actually an assembly of n charges, and here with reference to some reference point O, these will have position vectors as R1, R2, R3 and Rn. Suppose we have this point here as P, at which we want to calculate the electric potential due to this assembly. So here we must first have the distance of this test point from individual charges. So for that reason I am just joining this point from every charges forming assembly. So let this we call it R1P. Now this would be R5P, this would be RNP, this would be R4P, and this distance has to be R3P, and finally this has to be R2P. Now we will be directly writing the electric potential at point P due to individual charges. So let's see the electric potential at P due to charge Q1 is, let me call this to be V1. So this V1 directly we can write 1 upon 4 pi epsilon naught source charge. Source charge is what? Q1 upon distance. Distance is R1P, R1P. Similarly, we can write potential due to Q2 at P, potential due to Q3 at P, and likewise. So similarly, we can write V2 to be equal to 1 upon 4 pi epsilon naught Q2 upon R2P, and in the similar way we can have V3 to be 1 upon 4 pi epsilon naught Q3 upon its R3P, and in the same way it's Vn equal to 1 upon 4 pi epsilon naught Qn upon Rnp. Now we can have superposition principle. So just adding these all, we can have total potential at that point. So hence potential due to this assembly we can write V equals to V1 plus V2 plus Vn. Now just placing what is common in all, 1 upon 4 pi epsilon naught. So you can just have that term common as a whole, and inside the bracket you can write Q1 upon R1P plus Q2 upon R2P plus Qn upon Rnp. So in abbreviated form we can write it to be 1 upon 4 pi epsilon naught summation over I equal to 1 to n Qi upon Rip. In terms of position vector, what can be written in terms of position vector? We can have potential to be equal to 1 upon 4 pi epsilon naught summation over I equal to 1 to n Qi upon mod of vector R minus vector Ri. So in terms of position vector we can write this. So that's it. Let's have next topic, electric potential at a point due to continuous charge distribution. As we had earlier, force due to continuous charge distribution, electric field intensity due to continuous charge distribution. So here we have electric potential due to those three types of, remember, three types: linear, surface, volume, charge distributions. Okay, so let's start. Suppose here actually we have a small element comprising charge dq and having a distance dr from a test point where the potential I am writing directly. So the potential at a point due to dq charge of small element. So we write this to be equals to V equals to 1 upon 4 pi epsilon naught 1 upon R, or you can directly write dq upon R. Fine with this? Okay, now if say the charge distribution is linear, line charge distribution is given. So first I am writing, in case of line charge distribution, in case of line charge distribution having linear charge density as lambda, or so that lambda will be written as dq upon dl. So for that dq we can write lambda into dl. So directly I am writing VL equals to 1 upon 4 pi epsilon naught integral over the whole length L lambda dl upon R. So this will be the potential in case of line charge density or linear charge. Now in case of surface charge distribution, here actually if we are given surface charge distribution, then the potential can be written as Vs equal to 1 upon 4 pi epsilon naught integral over the whole surface as sigma ds, surface charge density times small area, upon R. Now for the last case, third, we can have third case if the charge distribution is given to be volume. In case of volume charge distribution we can have where the volume charge density is taken as rho. So rho dV will be the amount of charge present on that small element. So here rho dV will be written. So we write VV equals to 1 upon 4 pi epsilon naught integral over the whole volume V. So rho dV upon R. So this is the volume charge due to volume charge distribution potential at certain point. Now for the next case, now if these all three types of charge distributions are given simultaneous to us, so in that case what is the potential? In case of having all three types of distribution of charge simultaneously, then the potential can be the sum, that is VL plus Vs plus Vv we can write, and here we can have 1 upon 4 pi epsilon naught as common, and inside you can write integral over L lambda dl upon R plus integral over S sigma ds upon R plus integral over V rho dV upon R. So these are this thing. Now if say along with these all three types of charge distribution, there are certain discrete charge distribution as well given. So in that case what can we write? For the fifth case, so here I am directly writing potential will be written as 1 upon 4 pi epsilon naught. Now in case of discrete charge distribution you can have integral summation over I equal to 1 to n Qi upon Ri plus, these all three terms. So integral over L lambda dl upon R plus integral over S sigma ds upon R plus integral over V rho dV upon R. So this thing will be the potential, total potential due to line, surface and volume along with few discrete charge distribution. So with this we end up today's session, students. Do like and subscribe the channel.